Welcome to the video lecture for section 5.1 on areas and integrals. We're going to begin the study of Calculus 2 with the discussion related to integrals. You should be very familiar from Calc 1 with the idea of a derivative. And you should also know, as it says here, that the derivative of position is velocity. What if you know the velocity and you want to go backwards and find out information about position? Specifically, how far you traveled from one position to another. So that leads us naturally to the question of how can we reverse the differentiation process? This is a basic concept that you already understand. Consider this. Suppose a train moves along a track at a steady rate of 75 miles per hour from 7 a.m. to 9 a.m. What's the total distance traveled by the train? You're familiar with the idea that distance is a rate times a time. So if I want to know the distance that my train traveled, I can take the rate of speed, which is the 75 miles per hour, times the time that I was traveling. Now, if I traveled from 7 a.m. to 9 a.m., that's 2 hours. And when you multiply miles per hour times hours, those hours cancel out. And you're left with 75 times 2 is 150 miles. Now let's think about this graphically. If my train starts out at 7 a.m. traveling 75 miles an hour, that would be located here on my graph. It does this until 9 a.m. I'm going to create a rectangle out of it that extends down to the x-axis. What's the area of my rectangle? Well, it's length times width. The width of my rectangle is 2 units, and the length of my rectangle is the length of this side, which is 75. So to calculate the area of my rectangle, I would take length of 75 times width of 2, and notice I come up with the same number. It's 150 square units. And this isn't a coincidence. If we know the position, and we take the derivative of it, because a derivative is a rate of change, we end up finding out the velocity of the object. Well, if we go backwards, if we start with the velocity and want to know the position, that's known as integrating. And it involves finding what we call the area under the curve. Now, in this case, yes, our curve was just this little straight line segment. Curve is just more general. And when I say area under the curve, and the area under the curve, what I mean by that is the area that exists between my function, which in this case was a velocity function, and the x-axis. It's the amount of space in that region. So here's your formal definition that states that if you have a function defined over a certain interval from a to b, the expression, this long stretched out s, which actually comes from the word summation, you'll find out why, from a to b represents the integral from a to b of f of x dx. Now, we'll understand this notation a little bit more, but for the time being, kind of just allow this dx to hang out there. Essentially, it's a length times a width, okay? Now, this expression denotes the signed area bound by the vertical lines. So you kind of cut off your function from one vertical point A to another vertical point B. You have the function and the x-axis. And it is considered to be a signed area. Hopefully you're familiar with the idea that velocity can be negative because it indicates the direction of travel. Well, when we work with integrals, we do consider signed areas, and it is always the areas below the x-axis that count as negative areas. In example 1, two shaded regions labeled as integrals appear below. We're going to use familiar area formulas to evaluate the integral. So in area 1, we have the integral from 1 to 3 of f of x dx. This means find the area of this shape that is bounded by the vertical lines 1 and 3 and located below the function to the x-axis. And the way that we're going to do that is we've been asked to use familiar area formulas. What shape is the blue shaded region? It's a trapezoid. And you should be familiar with the area formula for a trapezoid, which is just 1/2 height times the sum of the bases. Now, by looking at my graph, I am able to determine that the height of the trapezoid, remember the bases are the parallel sides, so the height is here from 1 to 3, which is a total of 2 units. The bases are the lengths of the parallel sides. The one on the left is 2 units long, and the one on the right is 4 units long. So I have a 2 plus 4. And when you multiply this together, half of 2 is 1. 2 plus 4 is going to be 6, so 1 times 6 is a total of 6 square units of area. And so that's the value of this integral. Let's take a look at the next one. We're asked to integrate from 0 to 4 the function h of x dx. So we are supposed to look at the region from the vertical line x equals 0 to the vertical line x equals 4, which is here to here, and consider that portion of the shaded area that is below the function h of x, and h of x is this weird curve followed by a straight line. So the area between that and the x-axis. All right, well, what shape is that? Okay, that's obviously not a standard shape. So what I'm going to opt to do is I'm going to break it apart into familiar shapes. If I split it here, I can find the area of each individual part and then just add them together to get the value of the integral. So what are these two shapes? I've got shape A and shape B. Shape A is a quarter of a circle. And to that, I'm going to add the area of shape B, which is a triangle. The value of my integral is going to be the area for 1/4 of a circle. So 1/4 pi r squared. To that, I'm going to add the area of the triangle, which is found by computing 1/2 base times height. Now I substitute the value of the radius. The radius of the full circle, if it existed, would be 3 units. You can see it right here along the x-axis. So the radius is 3. And for my little triangle there, the base is from 3 to 4, which is 1 unit, and the height is here from 0 to 3, which is 3 units. So base of 1, height of 3. Now we have 1/4 pi times 9 plus half of 1 times 3 is 3, so it's 3/2. Simplifying just a little bit here, 9 times 1/4 is going to be 9/4 pi plus 3/2. Now, if you wanted to, you should be able to pick up a calculator and get a decimal approximation for that. I'm not concerned about that. We'll just leave it in its exact value format. So this is the area of that shaded region, and the area of the shaded region is the value of the integral. So going back to the train example, what if our velocity function wasn't straight? What if it actually was a curve? It wasn't constant, in other words. Familiar area formulas are not super helpful in those situations. So for now, if we need to calculate a shaded area to find the value of an integral, we can count roughly the squares in the shaded area. You have to make sure that you pay attention to the area of a single square on your graph, because your x and y axes can be labeled in a variety of ways, so you must pay attention to the scale. Let's check out example 2. f of x is the function 1 minus x squared, and we're asked to estimate the value for the integrals below. Area 1. We want to estimate the integral from 0 to 2 of f of x dx. Now notice that area has been shaded for us. Starting at 0 to 2, we shade from the function to the x-axis. Now from 1 to 2, that means we're shading actually from the function back up to the x-axis. Your shaded area, your integral, is always the area between your curve, your function, and the x-axis. Next, we're going to estimate the number of square units in each shaded section. All right, so the area of this first little piece, I'm going to say that that looks like 2/3 of a square. Now the next area, I'm going to estimate, you've got this square here, and you can kind of take this little blue guy from down here, kind of finish that off. I'm going to say it's somewhere around 1.5 or 3/2 of a square. Now again, I can total up these areas and find out the value of my integral. However, this is where you need to keep this previous note in mind, that we always work with signed areas when we're working with integrals. Areas below the x-axis count as a negative area. So when I'm calculating this, I consider this area to be -3/2 squares. So area 1 will equal, I'm going to take the number of squares in the part above the x-axis, add to it the area of the squares below the x-axis, keeping in mind that they're negative. I'm going to get a common denominator for my fractions here, which would be 6. And I find out that the area is composed of -5/6 squares. It should make sense to you that the overall answer is negative because there's more shaded area below the x-axis than there is above the x-axis. However, that's not my final answer. You need to, when you're calculating that area, always make sure that you take the number of squares and multiply it by the area of a single square. Now the area of 1 square, when you look at this graph, this is 1 unit by 1 unit. So the area of a single square is just going to be 1 square unit. But this is where you have to be careful, because if your scale was different, for instance, if this x-axis went by 5 units, then one little box would actually represent 5 units on one side, 1 on the other, and it would be equivalent to 5 square units. In any case, if I have -5/6 squares and each one of those is 1 unit square, multiply those together, and my area will be -5/6 square units. Now for the next graph, we want to evaluate the integral from -2 to +2 of f of x dx. So you can see we've gone from -2, shaded the area between the curve and the x-axis, curve x-axis, curve x-axis, and curve x-axis. We can take advantage of the symmetry of this curve. We know that the combined area of these two sections turns out to be -5/6 square units. There are identical regions on the other side of the y-axis. There's an equal size positive section and an equal size negative section. So to calculate area 2, we just need to double our last answer, which gives us -10/6 square units, or if we reduce it, -5/3 square units. So to recap what we've looked at so far, if your area under the curve can be defined in terms of simple geometric shapes, we prefer using formulas to calculate exact values. If your areas defined by your curve are not convenient geometric shapes, we just fall back on counting the squares, keeping in mind the value of a single square on the graph. Now, there are a couple of properties you need to be aware of when you're working with integrals. This theorem says f and g have to be continuous functions. We'll get into that more later, but for now, make sure you understand that those are the nice, well-defined, well-behaved functions. They're smooth. You can trace from one side to the other without lifting up your pencil. K is going to be a real constant, so just a number. Then we have a sum rule for integrals. If you have two functions that are being added together, the sum rule says, when you're trying to find the area from A to B, you can find the area of the first function and just add to it the area of the second function. Notice this is a plus minus sign because you also get sort of the difference rule for free. If your functions are being subtracted and you want their areas, you can find their areas independently and subtract those areas. The constant multiple rule says that if you have a constant multiplying your function, you can take that value outside, find just the area of the function itself, and multiply it by the constant at the end. Next, we have a splitting the interval rule, which says between A and B, if you have a number C, and you want to find the integral from A to B, you can split it up. You can go from A to C first and C to B second. So in other words, that's kind of like looking at this graph. If I want to know the integral from A to B, where 0 is my A value and 2 is my B value, and I have this C value of 1 in the middle, I can find the integral from 0 to 1, and then I can add to it the integral from 1 to 2. And finally, this last rule, switching the lower and upper limits. If your B value is actually smaller than A, so, for instance, if A was 6 and B was actually a smaller number, like 2, think about what that would mean. We have seen back up here, when we write 0 as a lower limit and 2 as the upper limit, we mean start at 0, go to 2. What does it mean if those switch places? If I write the integral going from 2 to 0, effectively what I'm doing is I'm reading backwards. I'm starting at 2 and going to 0. So instead of reading left to right with my integral, I'm reading right to left, and that does have an impact. The impact that it has is it's the negation. It's whatever your integral value was when you went forwards, but negated. So again, if I use the numbers I started with here, if A was 6 and B is 2, that backwards integral is the same as going forwards from 2 to 6, but we're going to make it negative. So in other words, areas below the x-axis, we already said, are negative areas. Well, if you read from right to left, you are also calculating the negative area. And finally, let's check out this example. This is not in your text as it says, but I'm given two pieces of information. That the area under the curve, f of x, from 0 to 5 is equal to 10, and the area under the curve from 5 to 7 is 3. And I'm asked to find various other integrals. This is possible using the properties listed up above. Letter A asks us to find the value of the integral from 0 to 7 of f of x. This is the same as finding the integral from 0 to 5 of f of x, knowing that area, and then adding on to it the area from 5 to 7. And you'll notice conveniently those are the values that were given. So to find the value of my integral, I just add the two areas together. An area of 10 plus an area of 3 gives us a final value of 13 for this integral. Now B, notice the limits have been switched from how one of our integrals was given up above. What's the effect on the area when we switch the limits? Well, if reading from left to right, 0 to 5, the area is 10, When you read right to left, the area is negative. Or if you want to write it out in symbols, this integral can be rewritten as negative. Switch the limits on your integral. Letter C is one I encourage you to think about in terms of the geometry. If you have a function, let's say this one here, and you want to calculate an integral starting at a value and ending at that same value, think about what that would mean. If I start at 0 and end at 1, I understand that I'm computing this area. If I start at 0 and I end at 0, how much area exists? The answer should strike you as being 0 because you haven't got any width to your shape. Therefore, whenever your upper and lower limits are the same, the value of your integral will be 0. Letter D is an example where I've got a constant multiplying a function, and the rule above says that we are allowed to take that constant in front of the integral. I have already calculated this integral, 5 to 0, in letter B, and found it was negative 10. So my final answer here will be 2 times negative 10, which is negative 20. And last, this is just another example of the constant multiple rule. I can take the constant out in front, calculate what the shaded area is for the integral, and from 0 to 5, we were told that the area is 10. 3 times 10 is 30. Now, after completing this video, I would encourage you to go through and read the portions of the textbook that are listed on the assignment page and just clarify anything that you need clarified before attempting the homework.